welcome back. We're going to talk about colligative properties today. So we're almost towards the end of our notes on our solutions unit. Let me just hide my meeting controls over there and get myself my slideshow presented here. All right, and duplicate slideshow. Okay, so what are colligative properties? All right, so the term colligative properties are properties of solutions that depend on the concentration of the particles present and not necessarily the type of the particle. So concentration, right, the amount, oh, I don't like that red with green, I got it right. The amount of the concentration particles, so let's go with green, right? So how much, right, amount. So how much particles are present in the solution. Okay, so what is dissociation, right? It means to separate from each other, right? If I'm disassociating from an organization, it means I'm separating from that organization. All right, so when ionic solids, remember ionic is a metal plus a non-metal, right? Or when you have a polyatomic ion present, break apart into ions, all right? So into ions. That's what is dissociation. Molecular substances, which are called covalent substances, right? Covalent is molecular, and which is where we only have nonmetals only, do not dissociate. So let's take a look at an example. So when I have magnesium chloride, I know this is an ionic compound because I have magnesium, which is a metal, and I have chlorine, which is a nonmetal. And so when this disassociates in water, right, so when I dissolve magnesium chloride in water, it splits into the magnesium ion and it splits into two chloride ions. So then how many ions are present in solution? This is 3 ions total, right? 3 ions that are aqueous in solution. And if I have, the lithium sulfate, right? I have a metal and a polyatomic ion. This is an ionic bond between those two, right? Remember, when we have a polyatomic ion present, that means we have both ionic and covalent bonds, right? We have ionic between the positive lithium and the negative sulfate, and then the covalent bond is between the sulfur and the oxygen. So when this dissolves into solution, right, I have an aqueous 2 lithium ions that are positively 1 charged, and then I have 1 sulfate ion that's a negative 2 charge. So again, I have 3 ions present, right, 2 lithiums and 1 sulfate. So now let's look at glucose over here. I have carbon is a nonmetal, hydrogen is a nonmetal, oxygen is a nonmetal. So this means that I have a molecular substance. It does not dissociate, so it's only one thing in solution. It sticks together. It does not dissociate. So if I have sodium and bromine, right? So again, I have a metal and a nonmetal, so I have an ionic bond. And it splits into sodium and bromine, right? So now I have 1 sodium and 1 bromine. I have now 2 ions that are present in the solution, aqueous ions. So a colligative property depends on the number of particles present. So if this only has 1 particle present, right, because it doesn't dissociate, these ones are going to exhibit the most impact of colligative properties. And then this one with only 2 ions would be less of an impact than the magnesium chloride or the lithium sulfate. And so what does this mean in terms of what are these impacts that we're talking about? So the first one that we're talking about is freezing point depression. So this means that when the solute is dissolved, it will depress or lower the normal freezing point. And so the amount the freezing point is lowered by dissolved substances depends on 2 factors. The concentration of the solute, right? So that's going to be like our molarity or our parts per million percent composition, and the nature of the solvent. And so what's with this little salt truck here? We live in Syracuse. Why do we put salt on the roads? So let's look at our sodium chloride solid, right? So when that sodium chloride solid dissolves in water, it ends up splitting into the aqueous sodium ions and the negative chloride ions. And so I have two ions present in solution, and these ions lower the freezing point of water. So the freezing point goes down. And I like to remember this, I'm just going to write this up here, that the F points down, right? So the freezing point goes down, right? So F freezing goes down. So the salt on the roads lowers the freezing point of water so the ice won't be able to form. The salt doesn't necessarily melt the ice, it lowers the freezing point so that the water cannot freeze. It interferes with the freezing because these ions are colligative properties. The more ions you have, the lower the freezing point, right? So let's go right over here. So the more ions will be the lower freezing point. And then I'll just do freeze point. So if I'm comparing sodium chloride, let's compare sodium chloride to magnesium chloride. Which one is going to have the lowest freezing point? Would be the one with the most ions, right? So whichever one has the most ions. Which one has the most ions? Well, sodium chloride has two ions, sodium and chlorine. Magnesium chloride has one magnesium and two chlorines, so then this has three ions. And so magnesium chloride would have the lowest freezing point when added to water. It would lower the freezing point of water more than sodium chloride because it has more ions. So now we have boiling point elevation, right? Elevation means up, right? Elevators go up. So I like to do a B for boiling, pointing up. So remember I had the freezing point, right? Freeze down, boiling point goes up, right? They do opposites, and this is the same effect. It's a colligative property. When the solute is dissolved, it is going to raise the normal boiling point, right? Water's normal boiling point is 100. We add some solute in there, the boiling point is going to go up. So the amount the boiling point increases or elevates is by dissolved substances depends again on two factors. The concentration of our solute, right? The more we add, the higher the boiling point, and the nature of the solvent. And so here we have some water boiling, and this is some salt water, We often add salt to pasta water when we're making pasta for two reasons. Well, one, it's an opportunity to add some flavor to the pasta as pasta is cooking. And two, we are elevating the boiling point of the water so that it's cooking at a little bit of a higher temperature. So instead of boiling at 100 degrees, water will boil at above 100 degrees because the boiling point goes up. So adding sugar to water will do the same thing. It's going to raise the boiling point 100 degrees Celsius. And this is actually not salt water, this is sugar water. I forgot that we were talking about sugar here. So this is sugar water. This is important in making candy, right? So which is making like crystals of sugar. So adding the sugar to water. So if I have sugar, C6H12O6, and I compare that to sodium chloride, because I already talked about sodium chloride, let's talk about sodium chloride. When sodium chloride dissolves in water versus sugar dissolves in water, sodium chloride splits into ions, right? Because it's an ionic compound, metal and a nonmetal. So we have our aqueous sodium and chlorine ions. I have two ions present. And now C6H, so solid and solid. And so now when I'm dissolving sugar, sugar does not disassociate because it is a covalent, it is a molecular substance. So when it dissolves, it stays together as a molecule, but now dissolved in water. So now I only have one item, one molecule dissolved. So if I'm looking at which one is going to elevate the boiling point the most, sodium chloride is going to have a higher boiling point elevation when added to water as compared to sugar because of the presence of more items, more ions. Right, this is what colligative property means. right? It depends on the amount of the substance present. Right, and that wraps up. Time for doing some practice and some studying and making sure that you ask your teacher questions if you have questions. And I hope you enjoyed. Thank you for joining.